Hello, welcome to my talk titled Recent Advances in Unbiased Learning to Rank from Position-Biased Click Feedback. My name is Harry Oosterhuis. I'm an assistant professor at the Radboud University in Nijmegen, the Netherlands. And this is a talk that I've originally prepared for an internal presentation at Google, but which I would like to share with the rest of the world via this recording on YouTube. In this talk, I'll present 3 of my recent publications, 2 of which are in my PhD thesis, the cover of which you can see right here, which are titled Policy-Aware Unbiased Learning to Rank for Top K Rankings, published together with Maarten de Rijke at SIGIR 2020. When inverse propensity scoring does not work, affine corrections for unbiased learning to rank, published together with Ali Vardasby and Maarten de Rijke at CRKM 2020, and Unifying Online and Counterfactual Learning to Rank, published together with Maarten de Rijke at Wisdom 2021. We received the Best Paper Award at this conference for this work, for which we are very grateful. And I want to thank Ali and Maarten for their help with these publications, of course. The reason I've picked these 3 publications is because there is a through line, the themes, so the ideas of the first two papers come back in the third work, as you'll see. So they're connected in that way. And in this talk, I would like to show you the connections so you get a better understanding of unbiased learning to rank. So I'll give a brief introduction into counterfactual learning to rank. If you want to know more in depth, I have other videos that are more expansive and go more in depth on the basic concepts. I'm going to assume that you have some knowledge of them, but I'll give a brief introduction here to freshen things up. Again, if you want to know more, I'll link some videos in the description. The goal in counterfactual learning to rank is to optimize a ranking model. That's a model that ranks items, so orders them in a way to display to users that matches the user preferences between items. So the ordering of the items should match what users would like to see based on historically logged user clicks. So we're limiting the data from which we can learn from click logs. This poses a challenge because clicks are biased indicators of preference. This means that there's other factors that are not relevance or preference, I'm going to use those words almost interchangeably, that also influence click behavior. So if we simply follow the clicks, we're not just following preference, we're also following other things. The existing solution has been to weight clicks to correct for position bias. What do I mean with position bias? Well, when you show a ranking to users, users tend not to examine every item in the list. So if you show them a results list, they're usually more likely to look at the top results than at the bottom results. What you see here is an eye tracking study. And what we see is that in this red blob here is that 100% of participants looked at the first 2 results, but in this blue shade down here is that less than 50% looked at the bottom result. So the number of clicks that these different items are going to get, we can already tell is going to be heavily affected by the position at which they were displayed. We know that 50% of users are not going to click on this item because they're probably not going to examine it in the first place before we know anything about this item at all, right? We don't know whether this is actually exactly what they're looking for. Just from where it's positioned, a lot of users are not going to look at it. This is, of course, a problem because we want to rank according to how good these items are, not to where they were placed when we were collecting clicks. This is where counterfactual learning to rank comes into play. This is exactly what it tries to do. And to do that, it makes some assumptions. So I'll start with some notation. I'm going to introduce what I call the policy oblivious estimator. That name is going to make more sense when I introduce the policy aware estimator later, but we've coined that term to contrast with it. For an item D, traditionally these were called documents, that's why the letter D is used, and a rank or position, I'm going to use those words interchangeably, K. So K is a place in the ranking or a place on screen where you can show an item, and D is one of the items that can be displayed. We're going to decompose the click probability according to what we call the rank-based examination model. The idea is that you can take the probability of a click, condition it on the position at which it was displayed and the content of the item, so that you first have the probability of examination only determined by the position, because if we think about this, the user is going to examine something to find out what's there. So before they do the examination, only the position can affect it. So they're going to look somewhere on screen. And then what we call the relevance or the preference, which is the probability of a click conditioned on examination and the item. So the assumption here is users are not going to click somewhere where they haven't looked. People tend not to click blindly on the screen. And when they examine an item, the actual content of the item is going to determine whether they click or not. So the position where it's on screen determines whether the user is going to look at it in the first place. And then when they look at it and examine it, then we get the probability of clicking that actually has to do with the preference of the user. So we would like to get rid of this examination part, right? We only want to get this relevance part, really. The common way of dealing with this that you'll see in the existing literature is to use inverse propensity scoring. The idea is that if you have n displayed rankings, you can get an estimate of the relevance of an item D by taking the average over all those rankings, looking at was this item clicked on this ranking, and how divided by the probability of examination on this ranking. Why does this work? Well, these clicks that we have here, this click signal, is sampled from the probability of a click conditioned on the rank in the document. So it's going to follow this model according to our assumption. If we divide by the examination probability, then we're basically dividing away this first part, and we're left with the probability, the conditional probability that we call the relevance, right? The preference. So we're removing the examination effect from our estimate. And so this is called inverse propensity scoring, or IPS for short. To give you a visualization, so for a query, in this case we have a ranking 1, 2, 3, 4, 5. Item 3 is clicked. If we know that 50% of users will examine item 3, so there's a 50% chance that it was examined, then we're going to reweigh this click to account for that probability by 1 divided by 0.5, which gives us a weight of 2. So we're going to weigh this click twice as much to compensate for the fact that half of users probably will not examine this item to begin with. And another way of thinking about this, if you go back to this eye tracking study, is we're applying the inverse transformation. So where the position removes half of the amount of users that will examine an item, we're going to multiply by 2 to remove that effect, basically. Okay. There's something that I've ignored so far. That's how do we know the probability of examination? So usually you can't do a eye tracking study. Instead, it's usually estimated via randomization. That means swapping some items, changing items between rankings, their position, and seeing the effect. Expectation maximization, if you cannot do randomization, where you try to estimate both the relevance and the bias model, and then you don't need this extremely accurate relevance model to get an accurate bias estimation. The dual learning objective has a similar intuition. For this talk, I'm going to assume that we know the bias exactly. So I'm going to ignore the bias estimation problem. If you're interested in that, again, we have other videos that go more into depth here. But for this talk, I'll assume we know this. Okay? With that said, that is the end of the introduction. I'll now get into the first paper, which is on top K ranking. The top K ranking setting is something that has been not really addressed by the early work in Unbiased learning to rank, but even though it's very relevant or very prevalent in search and recommendation. What is the top K setting? A top K setting is a setting where only K items can be displayed, but there are more than K items that can be ranked. So in this, over here in this visualization, we have 5 items, but only 4 items that can be displayed. So item 5 is never going to be examined by any user because it's not on screen. They can't actually see it. It's never there. This setting is very common in recommendation. For instance, if you're recommending products from a collection, you're probably not going to include every product that you have in the collection in your recommended list, because that would overwhelm the user. You usually show a small selection that's also ranked. Why is this a problem for the existing approach? Well, due to what we call item selection bias. Item selection bias is an extreme form of position bias where some items have a 0% probability of examination. In the top case setting, if your position is greater than k, then your probability of examination is going to be 0. Because users cannot see you because the item is not on screen, right? The existing approach that I've described in the introduction does not work in this setting. Why? Well, it relies on reweighting clicks. But there are no clicks on an item that cannot be examined. No one is ever going to click on item 5 in this example. So there's no clicks that we can reweigh to correct for the 0 probability. That's why you cannot correct for this with the previous approach. All right. So this is where our solution comes in, which is the novel policy-aware estimator. There are 2 main insights that we had. The first was that we can sample the rankings that are displayed when we're logging clicks from a stochastic policy, so a policy with some randomization. What this means is that even if you can't display all the items at once, you can give every item a non-zero probability of being in the top K. So every item has some probability of being in the top K, so some non-zero probability of being examined. And then you can condition the click probability on the policy. So here we have the probability of a click under logging policy pi on item D. We're going to sum over each possible position. What's the probability that the policy is going to display item D on this position, times how likely is it to be examined, and how likely is it to be on this position, and how likely is it to be clicked given that it's examined. So what we've done here is, over this side here is the same click probability that I've shown you before, but now we take the expectation over that click over the position of that click probability from the policy. So this is the expected click probability under the logging policy. All right. Given this new decomposition, we can apply the same strategy and weight clicks to get rid of this first part so that we're left with the probability of relevance. So the new policy-aware estimator is going to estimate the relevance of an item by going over the average of n displayed rankings, where each click is divided by the probability of examination under the policy. And the probability of examination under the policy is just, again, the expected examination given that the rank of the item is sampled from the logging policy. This is unbiased if every item has a non-zero chance of being displayed in the top K. So the previous estimator needs every item to be displayed in every ranking, whereas here we just need them to have a chance, a non-zero probability of being displayed, but we don't actually need to display them all at the same time. And this allows us to be unbiased even when we cannot display all the items at once. To give you a visualization. So here for this query we have 2 possible rankings, 1, 2, 3, 4, 5, and 1, 2, 3, 5, 4. So the last item that's displayed is being randomized between 4 and 5. There's an 80% probability that item 4 is going to be displayed as the last item, and a 20% probability that item 5 is going to be displayed. If we see a click on item 5, we're going to reweigh the click, but this time we're reweighing it to account for both the policy probability and the examination probability. So the policy probability here is 20%, and the examination probability is 40%. So the probability of examination under this policy is going to be 20% of 40%, 8%. The weight is thus 1 divided by 0.08, which is 12.5. So the weight here of 12.5 corrects for both the examination probability and the policy probability at the same time. That's the difference between the previous estimator, which would only correct for this probability and ignore the policy probability down here. Of course, we've done some experiments to evaluate our proposed method. And what we've done is a semi-synthetic setup based on commercial learning to rank datasets. So there are these datasets, Yahoo, WebScope, and MSLR Web30K, that have been used for the Yahoo search engine and the Bing search engine, respectively, that contain queries with pre-selected documents and labels indicating the relevance between these documents and queries, together with some features about both the documents and the queries. And they have been used in a real-world commercial search engine setting. They don't contain clicks, so we have to simulate those clicks. What we do first is we simulate a top K ranking setting. So we have a pre-trained production ranker, which is trained on a really small percentage of the data, the raw data, just the labels, so that we have a model that's pretty good but not optimal, so that we have some room for improvement. And we use this ranker to get top K rankings, and we simulate them both without randomization, where you just show the top K of this ranker, and with randomization. What we do is we show the top K minus 1, and then the last item is randomly selected from what's ever left, uniformly randomly. So this is an easy way to give every item a non-zero probability of being in the top K. We simulate for each data point, so for each point that you'll see in the next graphs, 100 million clicks based on the dataset labels where we add noise and position bias. So the model that I've shown you before, we've put in some parameters so that the clicks are actually a biased and noisy signal of relevance. This allows us to show that we can remove the effect of this position bias and this noise and hopefully retrieve the optimal model. Let's look at some results. So this is on the MSLR Web30K dataset. The metric is the average relevant position. The lower the better. And the number of displaced positions is what we vary on the x-axis. So each of these points here is done by a simulation where we did a top 1 ranking all the way to a top 80 ranking. The average number of documents per query here is over 100, so we never have a setting where we can display everything here, but you can see various degrees of item selection bias. This striped and dotted line here is the production ranker, so this is the performance that we start with when we're gathering clicks. This dotted line down here is the optimal model. In a simulation, we can calculate the optimal model, so we know what's possible on this data set. And this red line here is our method. And what's important is that it's always approximating the optimal model. It's always very close to the optimal model, regardless of the value of K. As you can see, it's very hardly affected by K. We're not entirely sure. There seems to be some variance, but K doesn't have a big influence on our estimator, which is not surprising because the theory predicts that it's unbiased with respect to K, the item selection bias. But we can see it very clearly here. If we contrast that with the other methods, we see a clear difference, right? So these are re-ranking baselines that re-rank what was displayed. And you can see that K has a very large effect, right? K can either make it, if there's a lot of item selection bias, very poor performance. If there's less so, the performance gets better. The policy oblivious estimators are less heavily affected, but they can't get near the optimal model. I want to note that some of these baselines use the same data as our method. So the randomization policy is the same for this cyan line for the re-rank baseline, this blue line for the policy oblivious baseline, and the red line. They all work with the same data. So it's not that you need randomization. It's not just that you need randomization to get rid of item selection bias. You need both randomization and an estimator that takes into account the effect of the randomization. It's the only way to deal with this bias. Here is a similar setting. Now we're dealing with NSG at 5. So the higher the better. Again, we vary K on the x-axis. This is the production model, and this dotted line here is the optimal model. It's very hard to see because the red line is very closely approximating the optimal model. So if we optimize using our estimator, we're almost always very, very closely approximating the optimal model, which is great, right? This shows us very clearly it doesn't matter what the K parameter is. It doesn't matter how much item selection bias you have. We're always going to approximate the optimal model closely. The other baselines, again, are very much affected by item selection bias, by the K parameter. Depending on where it is, performance will be. So if you have, if you're showing at least 50 documents, then you can get close to the optimal model. If you're showing less than that, you're most likely going to be very far away from the optimal model. So it shows us that there's a heavy effect of this item selection bias. I have one more graph here, which is where we vary the number of training clicks. So again, NDCG, but now the x-axis here is the number of training clicks. And what you can see is that the baselines converge very quickly. It's a typical sign of bias. So the clicks here are trained in a top 5 ranking setting, so K is 5. This clearly these baselines can't do very much here. Again, our method does reach optimal performance. We see the learning curve here. We've added the stripe line here. This is the same estimator with no cutoff. So this is if we apply the existing IPS approach when there's no item selection bias, when everything is shown. We can see the difference in learning curve here. And this shows you how much harder it is to learn from top 5 feedback, which makes sense because it's much less information. But they still converge at the same place. Yes. So it's still quite impressive that it reaches this performance, even though it can only show 5 items at once. All right. That concludes my presentation of the first paper, which was policy-aware unbiased learning to rank for top K rankings. The main takeaways here are the existing approach cannot correct for item selection bias, which means that it's not unbiased for in a top K ranking setting, which is very prevalent in recommendation. We have a novel policy-aware estimator that is unbiased, but only under mild randomization, not heavy randomization, but you need each item to have some probability of being in the top K. The way that it does this is by basing its propensities on the logging policy instead of individual rankings. So it's not just that you need randomization, you also need to base your propensities on that randomization. And by basing the propensities not on the individual rankings, but on the logging policy. Again, this is something that we'll see again in the third part of this presentation. I wanted to point out some related work at the Web Conference 2020 by Ovaisi et al. They use the Heckman two-stage method to deal with item selection bias. It's interesting because it's very different from the IPS approach. So if you're interested in that, check it out, of course. For now, I'll continue to part 2, which is about trust bias. So far, we've assumed this rank-based position model, the model that I've shown you before, where you can decompose the click probability into probability of examination and probability of relevance. The assumption here is that once a rank is examined, or an item at a rank is examined, it's treated the same by all the users. So if a user is examining an item at position 1 or an item at position 5, they're going to treat these items identically. The difference, of course, that we've modeled so far is that they're just less likely to examine the item at position 5 than at position 1. But this ignores the trust that users have in ranking systems. In popular recommendation and search systems, users really trust the system. And what happens is they're more likely to click on examined non-relevant items if they're ranked higher. What do we mean by that? Well, if you have, let's say the user is looking at a ranking and it's examining an item that's ranked number 1. It doesn't look relevant to the user, but if they trust the ranking system, if they trust the recommendation or search system, they might say, well, it doesn't seem relevant to me, but the system surely knows what it's doing, so I'm going to look at this item and click on it anyway, because I trust the system more than I trust what I see right now. That's less likely to happen on a much lower rank. So let's say at rank 10, a user is more likely to say, well, it doesn't look relevant to me. The system also places it at rank 10, so it's probably not relevant at all. So they're not going to click there. So you're more likely to see incorrect clicks at higher ranks than at lower ranks on top of the position bias. So this is after examination. And this situation is not covered by this model. This model assumes that is not the case, that they're always treated identically once they're examined. So in a 2019 web conference paper, Agarwal et al. Propose modeling the perceived relevance as a way of capturing this trust bias. And the idea here is that you model, you allow the model to have items that are ranked at higher positions to be more likely to be perceived as relevant. So they introduce these two parameters: the probability of clicking conditioned on relevance examination in the rank K. So we have epsilon plus here, K. This is the probability that a user is going to click on an item given that it's relevant and examined and displayed at position K, versus epsilon minus, which is the probability of clicking conditioned on the fact that it's not relevant, examined, and displayed at rank K. So what do we get? The probability of a click on an item D is now the probability of, so the probability of click on position K, item D, is probability of examination. So we still have position bias, that's still in this model, times the following summation, epsilon plus K, so the probability that someone's going to click given that it's relevant and examined, times the fact that it's relevant, so that how likely is the user to click if they examined an item and it's actually relevant, plus epsilon minus K times probability that's not relevant, so plus the probability that it's examined, not relevant, and still clicked. So the user in this model can click on items that are not relevant, and their probability of clicking on non-relevant items is going to vary for different ranks. So we can say people are more likely to click incorrectly at rank 1 than at rank 10, for instance, due to the trust of the user system. So we'll call this the trust bias model. In their paper, they try to fit this model, so to infer its parameters, from real-world user behavior. And they show that their model is better at predicting future user behavior than the previous position bias model, or the rank-based position bias model. These are the parameters that they find. So on the left here is the examination bias. So this is the examination probability. And they fitted it on Gmail and Google Drive as search data. And what we see here is that users are, according to the position bias model, very quickly stop examining. So the probability of examination drops very quickly. Whereas in the trust bias model, it drops much less rapidly. And then if we look at the other parameters, so this here is epsilon plus, we see that users are expected to always click on items if they're relevant and examined, regardless of where they are. The difference is very small. But the incorrect clicks, so the clicks on items that aren't actually relevant, vary largely, right? So initially, people have around a 70% chance of clicking on something, even though it's not relevant, and it drops down to under 10%. So what happens is that the position bias model thinks, well, people stop looking at it. People stop looking at items, stop examining. Whereas the trust bias model says, well, they're still examining, they're just less likely to click incorrectly. Because this model is better at predicting future user data, we may assume it's more likely that this is a more accurate or better captures user behavior than the previous model. What we do in the paper is we introduce a more compact notation. So we introduce the same equation but different notation. Probability of a click determined, conditioned on the rank and the item, is going to be an alpha parameter, which is unique per rank, times the probability of relevance, plus the beta parameter, which is also unique per rank. The alpha parameter is going to be the correlation between clicks and relevance. This is what it is. This is in the previous notation. It's going to turn into this value, which is the probability of examination and the difference between the click probabilities when something is relevant or not relevant, plus the beta parameter, which is sort of the click-through rate that you get from the trust. So just the base click-through rate, you might say, which is how likely is a user to examine the item and click on it if it's not relevant. So the beta parameter captures the clicks that you receive just from being displayed at a rank, or an item just being displayed at a rank. And the alpha parameter models how much of an increase in click probability do you get from being relevant at this rank. What we prove in the paper, I'm not going to repeat that proof here, is that it's impossible to correct for trust bias with IPS estimation. The gist of that proof is IPS applies a linear transformation, but the trust bias model is an affine transformation, as you can very clearly see here, because there's two parameters, one being added and one being multiplied. You cannot, except for trivial circumstances, if the beta parameters are always 0, for instance, in non-trivial circumstances, you cannot correct for an affine transformation with a linear transformation. As a result, you cannot correct for trust bias with IPS estimation. And we need a new estimator. We introduced a new estimator, which is quite straightforward, actually. It's just we realize that you can inverse the affine transformation, and this gives you an unbiased affine estimator. So again, if we have this click probability, we can very quickly get the probability of relevance by taking the probability of a click minus the beta parameter divided by the alpha parameter. This is just simple math, of course. But this shows us that we can create an unbiased affine estimator. If we want to estimate the relevance of a document from n displayed rankings, we can, again, take the average over the n displayed rankings, take the click signal, whether the item was clicked or not, minus the beta parameter for the item at that ranking. So this is the click probability that we expect it gets just from the rank, not from the relevance. And then what's left of this subtraction is then divided by the alpha parameter. So the correlation between the clicks and the relevance. This is unbiased, so we can quite easily prove that this is going to give us an unbiased estimate of the relevance. So we can correct for trust bias, but we need to apply an affine estimator. I'm going to leave it at that. There's more in the paper, of course, where we look at experimentally compare these with the previous approaches and show that it's better, etc. For now, I'm going to leave it at this to keep the talk shorter and move on to part 3. Unifying online and counterfactual learning to rank. So far, I've talked to you about counterfactual learning to rank. So, learning from historical click data. Traditionally, however, there's been a more broad classification of methods. The broader family, the biggest family here is unbiased learning to rank. The idea is we're going to learn from clicks while correcting for interaction biases. And in that field of unbiased learning to rank, there's two families. One is online learning to rank and counterfactual learning to rank. Both are, the goal for both is to correct for these interaction biases. Online learning to rank corrects for bias by randomizing results through online interventions. An online intervention means that the algorithm decides what ranking will be displayed. So it can change the rankings on which we will observe clicks. And it can do randomization in those rankings to deal with bias. Counterfactual learning to rank, what I've talked about so far, cannot do this because we're working with historical data, so we can't change the data that we have. We're given click logs, we can't decide what's in those click logs. So we have to infer a model of bias. What we wanted to do in this paper is to bring these two families together to see online and counterfactual learning to rank, can this be brought closer together with the goal to unify it, because the methods that these two families apply are quite different, and intuitively that's a little strange. Why would you need different ways if the underlying problem is roughly the same? All right. Before, the first step that we did here was to look at the biases that previous work has addressed so far. And we identify three main biases, which I've introduced in this talk, right? We've started with position bias. Users are more likely to examine higher ranked results. We've seen the solution for that is inverse propensity scoring. Then I've introduced item selection bias, an extreme form of position bias where users cannot examine items at all because they're not displayed. So we have a 0% examination probability. A solution to this that we've introduced was policy-aware propensities, where you have a stochastic logging policy and then you base your propensities on the policy instead of the individual rankings. Then I've just introduced to you trust bias, which happens because users are more likely to incorrectly presume relevance of higher ranked results. The solution there is to apply the inverse of this affine transformation. So what we have here is we have three solutions. The policy-aware solution corrects for item selection bias and position bias. The inverse affine transformations correct for trust bias and position bias. But we're missing a method that corrects for all three of these at once. So we introduced that with the intervention oblivious estimator. This is not the main point of the paper, but the first step. Again, the name is chosen to contrast with what we really want to propose, which is the intervention aware estimator. But we'll start here because it's an easier step in between. The starting assumption is that clicks follow the affine model that I've described to you before, where we have this alpha parameter per position and this beta parameter per position. So we condition the click probability on the logging policy. This, again, is a trick that we saw in part 1, but we're now applying it to the affine click model. So again, we have the probability of a click conditioned on the item and the logging policy. We take the expectation over the different positions based on the logging policy, or how likely is this policy to place an item at each position, times how likely is at that position the item to be clicked, according to the affine click model. And we can rewrite this by saying, well, it's the expected value of alpha for item D on the click probability, under condition on item D and the logging policy, times the probability of relevance of this item, plus the expected value of beta for this item under the logging policy. So we have, this is a combination of the previous two tricks. We still have an affine transformation, but now we have the expected values conditioned on the policy instead of on the individual rankings, right? We can now introduce the intervention oblivious estimator, which applies the inverse transformation. So the probability of relevance is the probability of a click minus this expected beta value under the logging policy, if the click probability is also under the logging policy, divided by the expected alpha value of this item under the logging policy. And then you can create the estimator similar to you've seen before, but this is the intuition, and it's the combination of the two previous tricks. Basing the parameters by basing our transformation not just on the individual ranking, but conditioning it on the policy, and applying an affine transformation instead of a linear transformation like IPS, so that we can correct for trust bias. All right, I want to show, so this is unbiased, this estimator is unbiased, but it does behave in an unintuitive way when interventions take place. And to show you what I mean by that, I'm going to give you this visualization, an example of two policies. So on the left here we have logging policy 1. On the right we have logging policy 2. And they've been deployed for the same amount of time. So initially we had logging policy 1 being active, and then we had logging policy 2 being active. To make this example a little easier, I've set the beta parameters to 0. So what you can see here is The beta for document 1 and document 2, I'm only considering 2 documents, an example is 0 for both of these policies, so we can ignore the beta parameter. So the alpha parameter is going to be to indicate just the position bias, probability of examination. And under policy 1, it's going to be 0.1 for item 1. So there's a 10% chance that item 1 is going to be examined, and a 50% chance that item 2 is going to be examined. Now, the weights that the intervention oblivious estimator is going to give to these 2 documents when they're clicked will be based on the logging policy 1. So during this first initial period are going to be 10 for document 1, which is 1 divided by 0.1, and 2 for document 2, 1 divided by 0.5. So the clicks during the first period will get these 2 weights, but during the second period they're going to be different because now policy 2 was active, which has a 50% examination probability for both of these items. So now we're going to reweigh clicks for both of these items by 2. This is completely unbiased because these weights will do the inverse of what the bias is doing, so it's going to, in expectation, correct for the bias. However, intuitively, this is kind of strange, right? Because we know that overall, over the entire gathering of data, document 2 has an advantage over document 1. It always has a 50% probability of being examined, while document 1 initially has a 10% probability. So clearly document 2 has the advantage. However, during the second period of time, we're treating them as if they're equal, where we've forgotten about this initial period where it had a disadvantage. And the reason this is happening is because counterfactual learning to rank assumes there's just one logging policy that's collecting all of the data. But if if there an intervention takes place, it doesn't take that into account because it's not really a possibility that it's considered in the first place. What we wanted to do was to create an estimator that does take into account the possibility of interventions, the possibility that the logging policy changes. And we call that estimator the intervention-aware estimator. The first step here is to consider what is an intervention. Well, we call intervention any point the logging policy changes, or let's say is updated during the gathering of data. We're going to use the set pi, so capital Pi, to be a set containing all logging policies for each time step. So the set's going to be the policy for time step 1, 2, and so onwards for how long data was gathered. We're going to use a familiar trick. We're going to condition the click probability on this set now. So instead of conditioning it on the individual policy or the individual ranking, we're now going to the set of policies. So we have the probability of click on item D given the set of policies is, well, the expectation over sets, so how likely so the average over all of the average over the logging policy given this set. So we're taking the average over each logging policy to get the expectation here. And then we take, for each logging policy, the expectation over the rank, how likely is it to show the item at each rank, times how likely is an item to be clicked at each rank. So we have here the click probability given that the clicks were gathered using a set of policies instead of an individual policy. And again, we have an affine transformation. It's the expected value of alpha conditioned on the item and the set of policies times the probability of relevance of this item, plus the expected value of beta given this item and the set of policies. So this is very similar to the intervention oblivious estimator, but we're now looking at the click probability on the set level on the set of logging policies instead of the individual logging policies. We can again inverse this probability, right? We can get the probability of relevance here if we have the click probability based on the set minus the beta value based on the set divided by the alpha value based on the set of policies. So it's the same trick as before, but we're now applying it on the level of a set of logging policies instead of an individual logging policy, or as we did all the way in the start, on an individual ranking. Now, if we go back to this example that I visualized earlier, the main difference is there's going to be one weight for this entire situation. We're not going to weight the clicks in this initial period different than in the second period. They all get the same weight. And the weight is based on the expected alpha value, right? So it's, because these are employed for the same amount of time, it's just going to be the average between these two numbers, right? It's going to be 0.1 plus 0.5 divided by 2. If we do that, we get the weight of 3 plus 1/3 for document 1 and 2 for document 2. So this is also unbiased. We can prove that this is completely unbiased, but the difference is that we've now have one weight per document instead of different weights for each logging policy and document combination. Item combination, I should say. I'm sorry, it's an old habit. And that the resulting weight is much smaller or equal to what we've seen before. So in the previous example, we had a weight of 10 for document 1 here. It's now 3 plus 1/3. So the most extreme values of the weights are always going to be lower. To give you another example, here we have an example where an intervention takes place at t is 100. So we have a logging policy 1 up to 100 that gives a 25% probability to an item, and then after 100 gives a, what is this? This is a 5% probability of examination afterwards. And what this orange line here is it's a running average. It's the expected alpha value of the set so far. So it starts at the same number, 0.25%, but then slowly drops towards 5%, but it drops slowly. It doesn't drop down immediately, but slowly. The difference is even bigger if we look at the inverse. So if we take 1 divided by these values, we see that in the intervention oblivious estimator, we're going to go from a weight of 4 all the way up to a weight of 20 out of nowhere. So these clicks will be weighted by 20, and these clicks will be weighted by 4, whereas the policy aware estimator is going to weight all of the clicks slowly by a slowly increasing number. And we see it's much smaller than these other numbers. Why is this important? Well, we know from IPS estimators that if your weight if the weight for a data point, the maximum weight for a data point is larger, you have more variance. So if we can reduce the size of the weights, the average size of the weights, we can greatly reduce the variance. To show you what that means, we're going to look at the results. So again, we have a semi-synthetic setup, this time based on Yahoo. We use an affine top 5 click model, and we're using the parameters that I've shown you before, that were inferred by Agarwal et al. So these are based on real-world user behavior. So it's sort of the closest we can get to real user behavior in a simulation. And we use both counterfactual and online experiments. We apply these online interventions to the counterfactual methods in a logarithmic scale. We'll start in the counterfactual setting. So NCG at 5, the higher the better. This dotted line here is the optimal model, and the shaded areas are confidence intervals. I think we're talking 90% confidence intervals here. And what we see is not that exciting. We see the affine estimator, if we'd use it for optimization, or the policy aware estimator used for optimization, the model that we learn is not as good as the intervention aware estimator. This is not a surprise because it's the only unbiased estimator in this setting. I should note the intervention oblivious estimator is not displayed because there's no interventions. It's equivalent to the intervention aware estimator. So it would be the same line as the red line. But when we do have interventions, so in this case 50 interventions spread logarithmically, so in this kind of fashion, we see something very different. Whereas before, I'll go back to the previous slide, the intervention aware estimator could not converge on the optimal model after 100 million clicks. It now converges near the optimal model at 1 million clicks. So it learns much faster. These interventions really help. So the first lesson is interventions can really speed up your learning. What we've done here, by the way, is each intervention we've replaced the logging policy with what we think is the best model so far. So the model that we learned with intervention-aware estimator up to that point becomes the logging policy. If we look at the other estimators, they also do better. They converge at a higher point. They learn faster, but they don't reach the performance of intervention-aware estimator, but they also, especially the intervention-oblivious estimator, have an enormous increase in variance. So what you see here is that on average, this is a higher performance than in the previous graph, but the confidence interval is so wide that you don't know whether you're going to have terrible performance or really good performance. So the lesson here is interventions really speed up your learning. You can converge much faster. However, if the estimator doesn't take into account the effect of the interventions, it's not going to help you that much. It can actually be detrimental. So you want both interventions and an estimator that takes them into account. Again, this is very similar to what we see with randomization earlier, right? Where you need randomization and an estimator that takes it into account. It's a similar conclusion, but now with interventions. I wanted to show you the effect of interventions, which is something that we looked at. The bottom graph here shows you the logging policy performance, the top graph, the performance of the model that we learned. And the intervention-aware estimator, they're all intervention-aware estimators, but here we have the counterfactual setting, so no updates. The logging policy stays the same. And then up here, this green striped line, you can see is the worst performing model. We can compare it with the blue line, which has one intervention at 100,000 queries. And you can see that it immediately results in higher performance, right? We can immediately learn a better model, but that effect sort of disappears as more data is gathered. And if we have 5 interventions, which is this orange line, so it has an intervention over here, 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 and here, that's enough to find the optimal model within 100 million clicks. So even a really small number of interventions can make a really large difference. The more interventions you have, the less of a difference it makes. It's sort of a diminishing return, but we still see really big improvements here. So this shows, again, interventions can really help, even if it's a small number of interventions. So that's a comparison so far with counterfactual estimators. I mentioned that there are also online learning to rank methods that start from the online perspective, where they actively intervene. We also wanted to compare with those methods. I don't want to go into too much detail, but the state of the art is pairwise differential gradient descent, which is this blue line over here. What you can see is that initially it performs somewhat better than the intervention-aware estimator, but after about 20,000 queries, which is a small number in any practical setting, we have performance that's comparable or no statistical difference with our intervention-aware estimator. So we have state-of-the-art online learning to rank performance, except for this small initial period where the difference isn't that large either. So far we've seen that the intervention-aware estimator is the best choice, clearly the best choice in the counterfactual setting compared to counterfactual estimators. Now it also seems to be able to provide online learning to rank performance on the state-of-the-art level. The next obvious question is, well, can we do the same for the online method? Can we take this online state-of-the-art method and apply it counterfactually? You can do that. Previous work has already noted that. But what it turns out is if you leave it running for a long amount of time, it can actually give you very unreliable performance. So this orange line here is the pairwise differential gradient descent with 100 interventions. I just shown you that the intervention-aware estimator with 100 interventions converges very nicely on the optimal model. This model seems to be doing very well, but then suddenly really starts to deviate from the optimal model. This is really bad, right? So your first thought might be, well, we can do early stopping somewhere, but this method is designed to be something that you can keep running forever. It's designed to be a method that's online that you just turn it on and it keeps learning forever and it keeps improving. If it turns out that that method actually doesn't continue to improve, that's a really big deal. That really means you should not be using it. And what we conclude here is that this method only seems to be reliable, empirically speaking, from what we can see from our simulations, when it's run fully online. If you can't run it fully online, don't use it. All right, that leaves me to the conclusion of this third part. So I've presented here a Unifying Online and Counterfactual Learning to Rank, which was our Wisdom 2020 paper. Again, we're very grateful for the Best Paper Award. The main takeaways here are, we introduced an intervention-aware estimator. It's the first estimator that is designed for both the setting where you have counterfactual learning to rank or online learning to rank. It's clearly the most reliable choice for counterfactual learning to rank, but we also see performance comparable to online learning to rank. It's comparable to state-of-the-art. I want to mention that the online learning to rank methods do not have the same theoretical guarantees as our estimator. So in theory, they're not very, they can't guarantee much. So we have stronger theoretical guarantees, and in terms of what we see empirically in the simulations, comparable performance. We've also seen that the pairwise differential gradient descent is not reliable when not applied fully online. So we would highly recommend avoiding this method if you can't apply it in a fully online setting. What that leaves us is with intervention-aware estimator is, it seems to be the first individual method that is the best choice for both online and counterfactual learning to rank. So first time we have one method that's the best for both of these scenarios. And this is very, very exciting because it has the potential of unifying these two fields. It could be that in a couple of years, we're no longer talking about online or counterfactual learning to rank. We just have one approach to unbiased learning to rank in general. And hopefully, this is the first step in that direction. But time will tell, of course. All right, with that, I want to wrap up the talk. I've presented to you these three papers. In the first paper, Policy-Aware Unbiased Learning to Rank for Top K rankings, I've shown you that if you want to deal with item selection bias, you should base your propensities not on individual rankings, but on logging policies. In the second part, I've talked about trust bias, and I've shown you that to deal with trust bias, you should use an affine estimator instead of IPS estimation. In the third talk, I've shown you first that you can combine these two strategies so that you have an affine estimator that's not based on individual rankings, but on the logging policy. And then we went another step further in order to consider whether an estimator could be designed for both online and counterfactual learning to rank by taking this estimator and basing it on a set of logging policies instead of individual logging policies. Same idea as before, but to the next level. And it seems that that leads to an estimator that is the best choice for both online and counterfactual learning to rank. Of course, this is a very big claim, and I think one publication is not enough to fully support it. So time will tell us whether this actually holds up, and perhaps in the future, we'll no longer talk about online and counterfactual learning to rank, but just about unbiased learning to rank and methods that work very well and very effectively in both of these scenarios. I want to thank you very much for coming to my talk and listening all the way through. I have to show my references, of course, and I hope to see you again for my next talk. Thank you very much, and have a nice day.